Alright, I'm gonna try to give a little bit of rundown on how to use the Fusion 360 component. So once you downloaded it, you basically want to first start modeling um, the the material that you were giving in part A. So we go to create a sketch, and for this case, I'm gonna use the front page, the front plane, and then from there, I'm going to click on it, and I'm gonna create a circle. And I'm gonna start with my with the aluminium since it's 40 millimeters. So I'm gonna make it 40, and then we know it's 200 millimeters long. So I'm gonna extend it, and to extrude, you basically just click E, or you can go up to this menu right here, and then I'm gonna do 200, and then I'm gonna click Enter, and then this is gonna represent your aluminium, and then now we wanna add the steel, which is 300 millimeters long. So we do the same thing. We create a sketch. Now we're gonna click on this plane and click on it, and then we're gonna actually turn off our body so that way um, or aluminum does not combine with our steel. So let's actually rename this body aluminum. I can't spell, so I'm gonna leave it like that, aluminum. Alright, now I'm gonna create the circle again. Start from the center point, and then in this case we're gonna go uh, 25 millimeters. We're gonna click enter, and then we're gonna extrude again. Then just make sure when you're extruding that you're going in the outwards direction rather than the inwards, because if you go inwards, then you're making a hole through the original body. So make sure you're not cutting through the aluminum, because then you'll get funky answers. Okay, so anyways, I'm gonna turn off my aluminum body again, because we don't want the bodies to combine together, because otherwise Fusion 360 just combines the body into one. So I'm gonna cancel that out, and then I'm gonna type in 300 millimeters. So click enter, and then undo that, and then this is gonna be called stainless steel. So as you can see, now we have our rod that we wanted to build in the first place, and now we have to analyze it. So for that case, we're gonna have to go to under design. Well, actually, we have to first specify our material properties. You can either do that in the simulation component, or you can do it in the design phase, which is what in the tab we are right now. So what I'm gonna do is I'm gonna do it in the design phase. So we're gonna make our aluminium, because right now it's some steel, which is what CAD does, or Fusion 360 automatically makes all the materials you make as steel. So we're gonna right click, and then we're gonna see physical materials, and then that should open a tab if my Fusion 360 doesn't crash. Okay, so as you can see, it's just the standard C steel. So our aluminum is a 6061 aluminum according to our project. Alright, so we're gonna go into metal, and then we're gonna look for aluminum 601. Let's see. Aluminum 60. We're gonna have to scroll down. There we go. It's right here. You're gonna drag it and make sure it's on the aluminum. And now that's aluminum. Okay, now we want to do our stainless steel component. So we're gonna look for 304 stainless steel. So we're gonna scroll down. 304. There we go. Alright. I think it should be this one, stainless steel 304. Alright, we're gonna drag it. And there we go. Alright. Then I'm just gonna make sure that I did this. Come on. There we go. I'm just gonna make sure that is correct. Yeah, I think that's right. Alright, we'll see. Okay, let me exit this out. I'm gonna click escape to exit out. Physical material. Alright, now we have our now we can actually apply the load. So we're gonna go to design, then we're gonna go under simulation, and from here we want to click on thermal stress, because that's what the homework asks us to do. Alright, we click on that, and we first have to go to the manage tab, because we're given that it's at 20 degrees Celsius. That's our starting point. So we're gonna go manage, and then go on settings, and then make sure your global free temperature is at 20 degrees Celsius, and we're gonna click OK. Now we're gonna apply the load. So you're gonna go under loads, and then under thermal loads, and then when you're on this page, just make sure you click on bodies, because if you do faces, it won't apply to the whole body, so it'll be like on a specific section of the rod, and we don't want that. So make sure you click on bodies and then click both of them. You can, whoops, yeah, there we go. Click both of them, and then the problem states that we increase the temperature to 80 degrees Celsius. So we're gonna type 80. All right, we're gonna click enter, and then from there, that should be everything that we need. So we can just click solve. Or did I do? Oh! I forgot to add. Okay, so we want to add constraints, otherwise our solution, we can't solve this. So we're gonna go to constraints. Then we're gonna constraint this end, or not the whole body. So this is where you want to make sure you want to constraint that end. You want to make sure you don't mess that up. Then constraint this end. The constraints basically act as a wall if the rod was in between two walls, which is what the problem is set up as. So we're gonna click OK, and then we're going to now do you see how the pre-check went to a green? So that means now we can actually solve the problem. Then we're gonna click solve, and then we're gonna solve the study. So we're gonna call this problem one, piece of 6, piece of 5, piece of 5, I think. Okay, piece of 5, and then M80. And we're gonna click save, and then it's gonna run through, and I'm gonna pause right now because you guys don't wanna wait for the simulation to run. So I'm gonna pause the recording. Alright, so once the study has gone, usually takes like about 3 minutes, 5 minutes. You find your stress, which you can click through here, and then apologies, I'm a little bit sick. You find that your max stress is about 461, and the minimum is about 28. And it looks like overall, like this part that we analyzed manually, which you should have gotten about like 220 MPa for the steel component, which I believe. Let me double check. Is that right? Yeah, the steel component. So steel should be the long part, and then our average yield that we found was 220 MPa, and as you can see here, we're like in the range between 220. So it looks like it appears that our hand solutions are pretty good. It fits with the simulation, and then we also find that the aluminum is supposed to be around 86 MPa, and then here we can see it's below 100, or a little bit above 100, but that's a little margin error. So it's pretty good overall. And then in this problem, they also want you to analyze the displacement. So you just have to do this. Well, first of all, you have to take a picture of this. That's what the preset is asking you to do. So take a picture of the stress, a screenshot, if that works. Yeah. And then from there, they also want you to do the displacement. So you click on the displacement, and then it also looks reasonable. So the simulation shows you results. And they also want us to, I believe, investigate the internal stresses by using the spec drop down and create point probes. I still don't really understand why they want us to do this, but basically to do this, you go to inspect, and then you can see you can create a point probe, which tells you like the specific stress or displacement. Let's go back to stress at that point. In our case, we're gonna start with using a slice plane, because they also want us to use a slice plane. So I'm gonna click on this, and then I'm just gonna put my slice planes on this axis, and then we'll see a bunch of arrows, and then let's see, I wanna just wanna analyze this like inward. I mean, there's not really a lot of interesting stuff. Let's see, what if we do it that inwards? That's kind of cool. Yeah. Okay. So we'll put this in inwards, and then we'll click OK. Or actually, that's not super cool, but actually, let me read this. To undo something you did, you press Control C the way. So that's what I did to undo my plane. So let me do this again. I'm just gonna put -1, so that way I can get some interesting things. So put -1 millimeters. Click OK. Now I'm gonna use the point probes, which tells me the specific stress at that point. So let's see, I want to get the highest stress, so I click here. So at that point, our stress is 450 MPa, and then we do another point probe, and then yeah, you see that, and then you just do this as many times as you want, and then you basically take a screenshot of this, and then you upload it with your homework. That's what Mark Levinson wants us to do. So you do that, and that's it. You take another screenshot of this, and I'm not sure how to like hide the point probes in the cross-sectional area, so I'm just gonna Control C everything, so that way I can do everything. So I'm gonna do Control C, Control C, Control C, and Control C. And then we're back with our original plane again. So we have that, and then in the next part of the problem, um, once you analyze all of this and include your screenshots, um, they want us to find the maximum temperature, which you could heat the entire system by ensuring a factor of 3 or 2. So you basically have to solve for the force first, and then like do this nasty algebra once again, and solve for t, and then you end up once you find the change of t, you find that the change of t is 28.1, and we know that our initial temperature was I think 28 degrees. So I guess they want us to find the maximum temperature. So whoops, I meant to put 48.1 degrees Celsius. So let me I have to change this in my piece. I just realized that. But basically, they want us to analyze our we find that to ensure a factor of safety 2, we can only heat up to 48.1 degrees maximum temperature, or the lowest negative 8.1 Celsius degrees. So now they want us to put this into MATLAB and see whether or not or hand calculations, which tells us that theoretically the highest temperature with a factor of safety 2 is 48.1 degrees Celsius. We have to see whether or not that's true on the simulation end. So you basically take this again, but well, to make it easier, actually, I'm gonna click Finish Results, and then I'm gonna create a clone study, so that way I don't have to undo the original thermal load that I applied. So I'm gonna click Clone Study, and this basically gets rid of all the loads that I applied beforehand. So now we're gonna do loads, then we're gonna do another thermal load, and then do the same thing with the bodies. You're gonna click on the body, click on both bodies. I'm not sure why it's not showing up. Come on. Why are you not showing up? Give me a sec. Oh, I guess I was incorrect. Making a well, now I know that too. So making a clone study does not get rid of the original thermal loads. So you're gonna have to change your load here. So you're gonna click on the edit section. And instead of being 80 degrees, we're gonna compare it to the 48.1 that we found before. So we're gonna do 48.1 Celsius, and we're gonna click enter, and we're basically gonna do the same thing again. We're gonna solve, and then solve your study, and then it's gonna run, and you're gonna have to wait like 5 minutes. And I'm gonna pause the video again, so that way it doesn't take forever. So let me pause this real quick. All right, we're back. The thing is finished. So you go to your results, you click on this again, and then when you see this, you're probably freaking out. Like you see your scale goes up to like 8. You're like, did I do my calculation wrong? Well, no, because we're actually focusing on this part, the steel rod, and as you can see from the color scale, it looks like we're at two safety factor 2, which is what our hand calculations told us. So it looks pretty right. And if you want to double make sure, then you can create a point probe, and then I'm gonna click on it, or you can, well, you don't have to click on it, but you can just like move it around, and you can see it's like 2.023, 2.0. It's like 2 all around the whole way, except for this little section, which is 1.9. But yeah, basically the whole way it's at a factor of safety 2, which basically means your hand calculations are correct, and it satisfies and it aligns with the simulation. And you basically take a screenshot of it again, and you end up finding that you're right. And that's basically the homework. The fusion isn't really that bad. It's just the algebra is the nasty part. But yeah, that's basically an introduction to the fusion. It's not too terrible, but I just figured to make a video so that way people know how to use the thermal load. So yeah, anyways, well thank you for coming, I guess, and goodbye.